and matter, and spectrometry is the interaction between matter and energy. So, introduction to mass spectrometry. Mass spectrometry is primarily used to determine the molar mass of a compound and the molecular formula as well. Remember that when we studied IR, we were trying to determine functional groups like aldehyde, ketone, carboxylic acid. But now we're going to elucidate molar masses and formulas for a compound. So how much does this compound weigh, and how many carbons, how many hydrogens, how many oxygens, how many nitrogens? That's the kind of information that we want to get from a mass spectrum. So in a mass spectrometer, what we do is we vaporize a compound. So that means we convert it into the gas phase. Then we ionize it. So we treat it in such a way that it becomes an ion. And then it's going to undergo what's called fragmentation. That means it's just going to blow apart. It's going to fall into pieces, okay? And then the masses of the ions are detected and graphed. It is very important that you understand that the only signals or peaks that we see in a mass spectrum are ions. They have to have a charge. If you don't have a charge, you're not going to see it in the mass spectrum. So the most common method of ionizing molecules is using something called electron impact. Really, all you do is you hit the molecule, or you bombard it with a beam of electrons that are really powerful. In terms of the amount of energy, 1600 kilocalories or 70 electron volts. I'm not going to ask you to memorize that. All you need to know is that we take a molecule, an organic molecule, and we hit it really hard with a beam of electrons. Pow! And we hit it so hard that what we do is we can eject an electron. Well, what happens when you lose an electron? Right? If a molecule loses an electron, it becomes a cation. If it loses an electron, since electrons are always paired in an organic molecule, you're going to be left over not only with a cation, but it's going to be a radical. Remember that a radical means that you have an unpaired electron. Now, what did I say on the last slide? I told you that the masses of the ions are what are detected and graphed. And so since this is an ion, you will be able to detect it in the mass spectrum because it is a cation. It is an ion. It will be detected and graphed. Now, the mass of the radical cation is going to be the exact same as the parent compound, right? This is our parent compound. You hit it with that high energy beam of electrons. You knock an electron off, but what do we know? We know that the mass of an electron is going to be essentially negligible compared to the mass of the rest of the compound. Why? Because electrons don't weigh nearly as much as protons and neutrons, okay? So the mass of the parent, okay, is going to be the same as the mass of the radical cation. It's like the mass doesn't change because we can negate the mass of the electron. If the radical cation, what we see in here after the parent lost an electron, if that remains intact, we call that the molecular ion. And you're going to hear me say molecular ion over and over and over. Sometimes I might call it the parent ion, but we represent it with a big M like that. Then we put a plus next to it and then a little dot, which means it's a radical. And that means it is the molecular ion. And that is what results when the parent loses that one electron to form a cation, a radical cation. Well, what's interesting about the radical cation, if you think about it, you take an organic molecule and you just rip indiscriminately, you hit it with electrons hard enough that it loses an electron, you've got that radical cation. Well, the radical cation can fall apart. It can just crumble, if you will, in a way. But what I mean is that it's going to fragment. It's going to break apart to give you a radical and a cation. So here, I know we haven't looked at what are called fishhook arrows. This curved arrow that I have in the yellow circle represents the flow or the movement of one electron. But the idea is this, is that it's going to break apart to give us a radical and a carbocation. Now, what did I tell you about fragments that are graphed and detected? They're only the charged fragments. So you would not see the radical in your mass spectrum, but you would see the carbocation. Now, the whole point here is that we're going to get all of these ions, whether they're radical cations or whether they're just cations like this carbocation, and they're going to be graphed, plotted with respect to their mass to charge ratio. Now, the charge of everything that we're going to see in Chemistry 3101 is always going to be +1. So if you divide anything, the m over z represents mass over charge. If your mass is over +1 all the time, it's always just going to be the mass. So that's all you need to worry about in Chemistry 3101. Are there cases where the charge changes to +2? Yeah, sure. We don't really look at those in Chemistry 3101. So again, we don't see any neutral fragments, only the charged fragments. Now you might be thinking, okay, let's see, where am I so far? I've taken a molecule, I hit it really hard with a beam of electrons, I knocked an electron out, I made a radical cation. That radical cation is unstable, it can fall apart, it can fragment. Well, the reason why mass spectrometry is so powerful is this, in a nutshell, is that it fragments in a predictable way. The molecule is going to fragment in a predictable way. So let's say one person runs the mass spectrum on cocaine, okay? And they run it in a laboratory in California. If there's a person in a lab in, let's say, Denmark, and they run the mass spectrum on cocaine, they're going to see the exact same thing in their mass spectrum. Why? Because the molecule is the same and it's going to fragment in a predictable way. So you're going to see the same mass spectrum over and over and over. So in a way, a mass spectrum is like a fingerprint of an organic molecule. That's why analytical chemists on crime shows like CSI or the Forensic Files, they talk about mass spectrometry all the time in those crime shows. If anybody here is interested in forensic science, the reason the mass spectrometry is so useful to forensic scientists is because they can analyze tissues or blood or urine or whatever. And by looking at the mass spectrum at different molecules that they find in different tissues, since those mass spectra are like a fingerprint, they can compare them to other mass spectra and they can say, hey, this person had Xanax, let's say, in their bloodstream, or this person, had, tetrahydrocannabinol in their system, right? Because we have a predictable fragmentation of an organic molecule. Well, let's look at this mass spectrum of the simplest possible organic molecule, which is methane, CH4. What do we see in the mass spectrum of methane that's shown over here? We see on the y-axis here, we have relative abundance. So what does that mean? It means that this peak here, this signal, is the most abundant. It has a mass over charge of 16. Well, when we're doing mass spectrometry, we're talking about low resolution mass spectrometry. And so the masses for the elements that we're going to see all the time in this class, and let me see if I can find a spot where I have some more space. Maybe, no, there's not a lot of space on any of these slides. Maybe right here. For a hydrogen atom, we're going to assume it has a mass of 1, no decimal places. For a carbon, it's going to have a mass of 12. A nitrogen has a mass of 14. An oxygen will have a mass of 16. A chlorine will have a mass of 35. A bromine will have a mass of 79. And a sulfur will have a mass of 32. So these are the masses that you're going to see me use when I do my math. Mr. Dion, why aren't you using 12.01? Mr. Dion, why aren't you using 1.0079, what I see on my periodic table? Why aren't you using, 35.45 like I see on my periodic table? Because we're talking about low resolution mass spectrometry. We do not look at decimal places. We only go to the ones place. So going back to that mass spectrum of methane, the simplest possible organic molecule, it is CH4. The mass of carbon is 12, plus each hydrogen, that is 1 times 4, which gives me a total mass of 16. When I take that methane molecule, which has a mass over charge of 16, a mass of 16, when I hit it with that high energy beam of electrons, and I make the radical cation, I see that my parent, has a mass of 16. So the mass spectrum tells me that the relative abundance, or the most abundant peak in the spectrum, is the radical cation of methane after it loses an electron. And that tallest peak in the spectrum, we call that the base peak. You're going to hear me usually say the base peak. Okay, so for methane, the base peak is the same thing as the parent ion. So this peak here is, this peak here is the molecular ion. Okay, and it has a mass over charge of 16, okay? If you don't follow me, I mean, look, you have 15 here. You move over one and you have 16, 17, 18, 19, 20, right? Okay, there we go. Well, what about those peaks at 15 and 14 that we saw back here, right? This is 15, this is 14, 13, 12. You know, where the heck did they come from? Well, they must have come from the fragmentation of the parent ion. Here's the radical cation that's formed after methane is hit with that high energy beam of electrons. Well, why couldn't a hydrogen radical come off of there to form this methyl carbocation? Well, that's going to have a mass of what? You've got one carbon, this is CH3. You've got one carbon that weighs 12, and then you've got 1 times 3. That gives you 15. So this should have a mass over charge of 15. So what happens is that other radicals can break off, other hydrogens can break off to give us other ions or signals or peaks with masses of 12, 13, and 14. So the take-home message is all these are just showing the molecule falling apart, okay? Now, if you're like, okay, wonderful, a molecule falls apart, great, okay, how does that help me as a student? Well, again, what we're going to see is we're going to analyze how the molecules fall apart, and we're going to be able to make some conclusions from those. So, like I told you, mass spectrometry will come up in crime shows quite a bit because it's so important in forensic science, not only for explosive detection, but for, let's say, you know, monitoring reactions, drug metabolism, what else here? All kinds of different ones, amino acid screening. You know, there's a million uses for mass spectrometry. Why? Because it's such a sensitive analytical method. All right. Another good one would be drug testing, water quality, right? Looking for contaminants in food. Again, mass spec would be a great way to determine the amount of, you know, let's say, I don't know, poison in water or something like that. Mass spec is a very sensitive technique, and so it would be good for doing that. Well, what about analyzing that parent ion, right? Remember the M plus, we called this the molecular ion. Molecular ion, okay, or the parent ion. If you take a look at the mass spec of benzene, so here's benzene, and you can grab a calculator if you want to help you out with a little bit of the math. Benzene is C6H6. So if you have 6 times 12, the mass of each carbon, plus 6 times 1, what does that give you? That gives you 72 plus 6, which gives you 78. Look at our mass spectrum. Here you have 75, 76, 70. I don't know why I'm going right to 78 in my mind. 77. But look at the molecular ion. It's at 78. It's at a mass over charge of 78. So in this case, our molecular ion is the base peak. Okay, the parent is the base peak, right? Base peak was the tallest peak. And you can see that benzene is actually a very stable compound. Are there fragments? Sure, there's some here, there's some here. But there aren't a lot of fragments compared to something like this. Wow, this molecule is called pentane. So this is pentane. If we tally up the molar mass of pentane, we have 5 carbons. So it's going to be 5 times 12 plus how many hydrogens are there going to be in pentane? If we have 2n plus 2, so that means it's going to be H12. So we have 12 times 1. We tally that up, we get 72. So if we make the radical cation and we look over here, we have 70, 71, okay, and then we have over here 72. So this is our mass over charge of 72, but this is supposed to be our molecular ion, but it's not the base peak, is it? Right? The molecular ion doesn't always have to be the base peak, right? Because base peak meant the tallest peak. This here is our base peak. Base peak. Could anybody tell me what the mass of the base peak is? And it's not a trick. I just want to see if you can read it. Could anybody tell me the mass of the base peak? You know, and you might have to zoom in here a little bit. The base peak is this one. Yeah, it's 43, exactly. So it goes 40, 41, 42, and then this is 44, and this is 45. So it's actually 43. This is a mass over charge, which is equal to 43. I like that. All right, there you go. So you can see that pentane actually fragments pretty easily. It falls apart like crazy. I mean, your molecular ion isn't even all that big. I mean, it's got peaks here. You got all kinds of them here. You get a bunch of them here. You get a bunch of them here. Now, again, if you're the kind of student whose wheels are always turning, you're always thinking, and if you're wondering, holy smokes, you mean I've got to analyze every one of these and every one of these? I mean, this is going to take me all year. I got to analyze all those. I've got to analyze. The reason I'm doing this is because it's crazy. I couldn't do it. Okay. You know, if you had to analyze all of those peaks, it would take you all night. So, what is a spectroscopist supposed to do? What's an organic chemistry student supposed to do? You're supposed to learn how to look for the low-hanging fruit, the most useful pieces of the spectrum, and that's the whole point of the introduction to mass spectrometry. All right. Okay. Before we move on to the next slide, which deals with what's called the nitrogen rule, I just want to show you one quick thing. If you notice, the molecular ion has a mass of 72, and the base peak has a mass of 43. If you take 72 and you subtract 43, you get 29. Okay? You get a mass of 29. So that tells you that when we went from here to here, okay, it's a loss of 29. Okay? Now that you're like, okay, great, cool, yeah, wonderful, thanks a lot. You might think it's not interesting now, but I'm going to explain to you where that loss of 29 came from in a few minutes. All right, let's talk a little bit more about the molecular ion. There's a really cool rule in organic chemistry called the nitrogen rule that we can get a lot of information from a parent ion or a molecular ion just by looking at its mass. Again, the mass over charge of the parent tells you the molar mass. So if we go back here to this spectrum, since our parent had a mass over charge of 72, it tells us that the mass must be 72. Yeah, and it was, okay. But if you have an odd mass, okay, if your mass is odd, so what would be an odd number? 73, 75, 77, right? If the mass is odd, what that means is that you've got an odd number of nitrogens in your molecule. It's kind of cool. If you think about it, you know, it's something you don't think about in general chemistry when you're tallying up all those molar masses. But if you have an organic molecule with an odd mass, it, my friend, will always have an odd number of nitrogens. What does that mean? 1, 3, 5, 7, so on and so forth. An even mass, well, what does an even mass mean then? Well, an even mass can mean a couple of things. It means that either you've got no nitrogen, okay, or you've got an even number of nitrogens in the molecule. If we go back to our pentane, I showed you how to calculate the molar mass of that. It was 72. What does 72 tell us? It told us that there's either no nitrogens in that molecule or an even number of them. Well, we know that there's none. Okay, if we go over to this molecule, which has one nitrogen in it, what's the molecular formula? Well, I'll save you the time. It's C4H11N. So that's 48 plus 11 plus 14. You take your calculator and you take 48 plus 11 plus 14, you get 73. 73 is an odd number, and we have an odd number of nitrogens in the molecule. Here you have a diamine. There's two amines in the same compound, two nitrogens. The molecular formula is C3H10N2. Here, if you tally everything up, you get 36 plus 10 plus 28, and it gives you 74. So that is called the nitrogen rule. So nitrogen rule. The very cool rule, and all mass spectroscopists and organic chemistry students, whenever they see a parent ion, that's the first thing they always think. Is the mass odd? Yes or no? Okay, and what information can I get from that? Well, for methane, you probably noticed that there's an M+1 peak. Okay, if you're very astute, you probably did notice that. Okay, and if you're thinking, well, if my mass over charge is 16. How in the hell do I get 17? Okay. Well, it's because of the isotope of carbon, right? Hopefully you remember that about 1% of all carbons, roughly, it's like 1.1% of them are carbon-13, right? So every one out of 100 carbons is going to have, a mass of 13, right? Carbon-13 weighs 13 instead of 12. So if this has a relative abundance of 100, right, your molecular ion, and there's only one carbon in the molecule, that means that 1% of them should give you, or should have carbon-13. So the height of that peak is about 1% as much as the other peak. Now, if you're like, okay, cool, but how does that help me as an organic chemistry student, Mr. Dion? Well, the way that it helps you is the more carbons that you have, the higher the N+1 peak is going to be, right? If you have decane, there's 10 carbons in decane. So that means we should have 10 times the number of or probability of having carbon-13. So that means the N+1 peak is going to be about 10% of the height of the base peak. And so what you can do is you can analyze the relative height of the N+1 peak to the molecular ion, and you can estimate, which is pretty cool, you can estimate how many carbon atoms are in the molecule. Now, I didn't pick out any problems from the book for us to do that cover this. Just give me a sec here. I don't know how to move this from my computer, but let me just take a quick peek here. If you look at our book, there's a good skill builder. It's skill builder 14.3. So yeah, it says it right here. So skill builder 14.3. And then I'd like you, and I'm pretty sure I assigned these problems, but just to be sure, I want you to try question 14.20 before coming to class tomorrow. It's not a difficult problem, and I don't like to say that in a class like organic chemistry, but once you get the hang of it, usually students will master it pretty quickly. One more thing I want to say, for your next exam, you are allowed to bring in a non-programmable calculator. Okay, so you can have a non-programmable. You can't bring in a TI-85 mainframe, Tetris capable computer where you can put in the whole textbook. Just a simple little calculator is all you need. And just a little non-programmable calculator. Doesn't even have to be a scientific calculator. And you can bring one into the next quiz. All right. Okay, so that was section 14.10 and the N+1 peak. Now let's talk about the N+2 peak. So if you remember earlier on, I told you that chlorine has a mass of 35 and that bromine has a mass of 79, right? I mentioned that, briefly a few minutes ago. But you can actually analyze the N+2 peak and you can determine whether you have chlorine or bromine in the molecule. Let me show you how you can do it, okay? We'll start with chlorine and then we'll do bromine after. So right now, we're just going to focus on chlorine. So chlorine has two abundant isotopes. I wouldn't expect you to remember this from general chemistry, no way. But I want you to have this memorized for organic chemistry 1 and for the lab because it's so handy. Chlorine 35 is about 3/4 of the isotopes, so 76%. The rest is chlorine 37. So if you have a compound like this molecule here, this is called chlorobenzene. Hey, look, it's got a chlorine in it. If you look at the molecular ion of this compound, okay, so if we look here, if this is 100, 111, 112, this is 113. What's this right here? This is 114. This peak here, this is the molecular ion, okay? But the 114, that's the molecular ion +2. So we put it in brackets and put +2 like that. Also, sometimes you'll see the molecular ion written like this, where they put the mass in a bracket. It depends, okay? But what does that mean, or where does this come from? Well, hold on. If 1/3 of my chlorines actually weigh twice, or actually have 2 more atomic mass units, they weigh 37, right? That means that 1/3 of this molecule, right, the mass of this molecule is 112. So my mass over charge is equal to 112. That means that 1/3 of them should have an N+2 ion. That's 114, right? So what's the take-home message? The take-home message is this. If I hadn't given you any of this information and you saw a parent ion and an N+2 that's 1/3 the height, Okay, I could even label it for you. Let's draw a green arrow. We'll put 1/3 height of the molecular ion, chlorine. Just like that, my friends. That's all you need. It's the only information, and you can say you've got chlorine in your molecule somewhere. Okay. Same thing with bromine. The difference is the relative abundance of the two isotopes. Bromine 79 and bromine 81 are what? It's almost 50-50. It's pretty much 1-to-1, 51-49, close enough. So what does that tell you? If you look at the mass of bromobenzene, okay, you can see that you have your molecular ion, you have your molecular ion here, but then if you go up 1, 2, so this is your molecular ion, okay, this is your M+2 ion. Look at the relative height of the peaks. They're in a 1-to-1 ratio. So we'll put here the molecular ion and the M+2 ion are about 1-to-1, therefore bromine present. All right, that's all there is to it. So we have our molecular ion, that's 156, and we have our M+2, which is 158. It's kind of hard to see on here, okay? But you can just tally it up quickly. You have C6H5Br. So if you take 6 times 12, it gives you 72 plus 5 plus 79 plus 5 plus 79, and it gives you 156, okay? And that would be your parent ion, right? The mass over charge, like that. Okay, so what was the conclusion of the last two slides? If you have an M+2 is 1/3 of the height of M+1. That means you've got chlorine present in the molecule. And if your M+2 is 1-to-1 ratio, or about the same height as your molecular ion, you've got bromine present. All right, there you go. Well, from there, let's talk about this fragmentation, because I told you that the fragmentation would be predictable. All right, and it is. You probably recognize this number from earlier on. Where is it? 29. You remember when we looked at the mass spectrum of pentane? Okay, we saw that the base peak actually had a height of base peak, and this is a few slides ago, was mass over charge equal to 43. Remember I asked you that. I look at my chat right now and it says 43, which was the molecular ion subtract 29. Where did that 29 come from? Well, if you lose a methyl radical weighs 15, okay? So M-15 means that you've lost a methyl. If you lose an ethyl radical, an ethyl weighs 29. So if you see M-29, what did that mean? That meant that you lost an ethyl. So that's what the base peak came from. It was the propyl cation, weighs 43. If you lose a propyl weighs 43, so the ethyl cation has a mass of 29. And if you lose 57, that's the loss of a butyl. And so the methyl cation weighs 15. And there you have it, my friends. So that's fragmentation. Now, what if we had something like this? Okay, so this is 2,2-dimethylpentane. If you saw that the molecular ion, okay, or the base peak, I should say, base peak, if your base peak was at M-43, well, I just told you that 43 was the loss of a propyl, and it's a good idea to memorize 15, 29, 43, 57, which are all odd numbers. This is a methyl. This is an ethyl. This is a propyl, right? And this is a butyl. I would memorize these because they come up so much. Well, if you lost 43, why would that be such an abundant fragment? Because you end up with a tertiary carbocation. And we know that a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary, which is more stable than a methyl carbocation. So the fragmentation is predictable because the most stable fragments are the ones that are going to be formed in the greatest abundance. There are a couple other types of fragmentation that you just kind of have to be aware of in this class. There's the fragmentation for an alcohol, and the fragmentation of an amine, and a fragmentation for a carbonyl, meaning a ketone or an aldehyde, and I'll show you what they are quickly. The first one is called an alpha cleavage of an alcohol, and an alpha cleavage can also happen on an amine. So if you look at the alcohol functional group, the carbon to which the alcohol or the oxygen is bound, we call that the alpha carbon. If you break between the alpha carbon and the next carbon, which you can call the beta carbon, if you break that bond, okay, you end up with a resonance stabilized cation, which is going to be detected. Okay, so you don't even have to be able to draw this mechanism at all. Okay, I could teach this to somebody who's only studied general chemistry. All you have to do is just break that bond where this line is here. You draw what's left over here. You calculate the mass, and that would be a clue that you've got an alcohol. Also, if you lose water, well, water is 2 times 1 for the hydrogen plus 16, so it has a mass of 18. If you lose 18, that is also a clue that you've got an alcohol. You can also have an alpha cleavage for an amine. It follows the exact same rationale. The carbon that the nitrogen is bound to, we call that the alpha carbon. If you have a cleavage between the alpha and the beta carbon, again, you don't even have to draw this mechanism. That is a clue that you've got an amine, but you would might have maybe an odd mass if you have an odd number of nitrogens. And the last one is what's called the McLafferty rearrangement. Now, this is a difficult mechanism. What you need to know is the fragment that is lost. So the fragment that is lost has an even mass. So whenever you see an even mass being lost, this is a clue that you've probably got an aldehyde or a ketone. Okay, so every other mass that we're going to see being lost is going to be an odd mass. So to summarize what I just showed you, which was pretty quick, if you lose 15, that's the loss of a methyl radical. 29 is ethyl, 43 is propyl, 57 is butyl, 18 is water, and if you lose an even mass that's not 18, it's probably a McLafferty rearrangement. So what does that mean? It means you've got a ketone or an aldehyde. These are the fragments you need to know. When I was doing my degree a long time ago, back in the 90s, I took a class on mass spectroscopy, and we had, probably a couple of hundred mass fragments, like a table with hundreds of these that we had to memorize. Okay, now if you're like, oh, you're so smart. No, I'm not. Okay, it's just that I had an entire semester to do it. Okay, because all we talked about was mass spec day in and day out. So I'm giving you, a couple of lectures on mass spec. So I expect you to know a couple of fragments. Okay, and again, the more that you practice mass spec, if you actually speak with somebody who's a mass spectroscopist, I mean, they know every fragment under the sun, and it's crazy, some of the fragments. And you know what? All those fragments that I learned way back when I was a student, I don't remember them all. I remember the most important ones, But looking at mass spectra is just like anything in life. The more that you look at it, the better memory you get for all the different fragments. But again, these are the ones that I want you to know in Chemistry 3101.